Hi, and welcome to my presentation on the use of deep learning in fine-grained image classification. I'm making this presentation on behalf of my experimental group, which includes myself, William Campbell, Muhammed Ashraf, and Arthur Weatherby. The aim of this presentation is to give a brief explanation of our current understanding of the problem, understanding of the data set, the approach that we took in our experiments, the experiments we've undertaken so far, conclusions we can draw from them, any limitations we've met, and future works that we will conduct in the week ahead. So the problem at hand is to take part in a Kaggle INAT challenge, the 2019 version of the challenge. The goal of the competition is to classify a large number of fine-grained categories by image classification neural network. The data presented is a very large data set of 265,213 images for training. The images have a large image resolution, and after some analysis by my team, we've discovered, much like many image classification tasks, there's a long-tail distribution in the data. So most image categories have a small frequency, and there's a small amount of categories with a high frequency in the data set. So this presents an issue for training our model. If you look at the data distribution here, you can see the large frequency for small amount of training classes. So what can happen in our model is that our model can be very well trained on for those specific classes and perform well on these class of images. However, for other image classes, it tends to perform very poorly, and we want good performance overall, since the aim of the set of the research is good accuracy over all data for any tests, which we will be tested on, as can be seen by the distribution of the validation set. So the proposal we're making is to use a pre-trained Inception v3 model that's being pre-trained on the ImageNet as a base for transfer learning. And we hypothesize that fine-tuning all layers of this network using the highest possible resolution data will yield the best performance. This idea comes from a study by Q and al. For Cornell, who won the previous version of the INAT in 2017 and presented a very well documented paper, which we have used to provide insight into steps to take. A second thing that they presented was an idea on dealing with the long-tail distribution and increasing performance using a simple redistribution of data. So we propose a two-step training scheme to deal with this. So the two-step training scheme is, the first step is you learn good feature representation with the unbalanced complete data set, and then have a second training with those previous weights using a balanced data set that we create using a TensorFlow function, and have a small learning rate. So this slowly transfers, we slowly transfer learned features and let the network rebalance on the newly distributed data. Additionally, we applied data augmentation techniques like random cropping the image size, color shifting, flipping, and rotating of the images. This decreased overfitting and just gives more images for our model to be trained on. So this is the program structure of the data augmentation technique that we propose to use initially. So it all relies on this image data generation function, which is in Keras and relatively easy to use. And all it does is create a train generator, a validation generator. And if we feed it the data from the JSONs provided by Kaggle, our deep network can be trained optimally. So the experiments carried out so far have led to less than optimal performance. So the best validation accuracy we've had is 0.537. However, due to many technical constraints, we still feel good about this. We learned that the Atom optimizer performs much better, and also we believe that we've tuned our model by changing batch size increasing the steps and epochs to a point where it has the optimal parameters, given that by increasing the batch size more, we got an overfit model. As you can see, with the training accuracy increasing, but the validation accuracy decreasing, which is characteristic of overfitting. So, conclusions that we drew from our experiments. So the trials conducted so far showed an increased trend in the accuracy with improved training parameters. Training tuning, as you would expect, but the actual performance of this took a long time, as we had to wait 12 hours for each run of the test on Spartan. The current best result is 0.537, as I said before, and we believe that there's potential for massive improvements by using high resolution images. So limitations that we've faced are the software library limitations. So we thought by using Keras as a highly or more abstracted version of TensorFlow, it would be a lot easier to implement many tests. However, it's proved problematic in implementing high resolution images. So hopefully by practicing a little more TensorFlow, we can do that in the future. Another limitation was the wide variation of available functions. So using external functions was limited by using Spartan, decreasing the ease of experimentation. So we couldn't access repositories from Spartan, for example, the image data generator, which Richard had implemented separately, so we still have that functionality in our model. However, we spent a lot of time trying to figure out how to do it. The other thing was the need to understand evolving techniques like the LR multiplier. The initial hyperparameter selection took a lot longer than we expected, so choosing learning rate, batch size, optimizers, and other parameters, and then just general debugging codes and setting up the environment when it wasn't local like most software that I've worked on previously. So future work for the next week. Primarily, we want to do the fine-tuning of the model with an adjusted, well-balanced data set under smaller learning rate. So hopefully this increases performance like it did for the previous winners. Additionally, we're going to try and use TensorFlow to implement an ability to increase input image resolution to our model, and then hopefully improve performance like we had predicted and hypothesized. If we were to work further on the project, we would try and implement other networks like Inception v4, which has shown very good performance. Thank you for listening.